Welcome to another CO2 Monday and the Refrigeration Mentor podcast. I'm your host, Trevor Matthews. Once again, I want to thank you all for taking the time to come and hang out with us every Monday to learn a little bit about CO2 and find out about new products, new guests, new solutions for CO2. This week, I got a special guest that I've met a few weeks ago. I guess a
Yeah,
couple months back. We started messaging back and forth, and now got you on here, Matteo. Iobbi from Frascold USA. I don't know if there's US. This is your US. You're from the US.
yeah,
You're living in the US in Jacksonville.
yes.
He's a CTO, and we're going to be diving into their compressor line. They got a big compressor line here in North America. They sell thousands of compressors here in North America. It's a compressor manufacturer that I don't really know a lot about. And since we started chatting, I've been doing some research, looking up their stuff, and man, there's a lot of cool stuff that they have. And we're going to be diving into this today. If you have any questions, please shoot it in the chat. Matteo, welcome to CO2 Mondays. How you doing?
Hi, Trevor. Thank you. Nice for having us.
I'm so excited to have this conversation because I always love to learn about new products and new things, especially compressors, because my background is compressors. I really got a good understanding of them, and I'm starting to learn more of all the other manufacturers, of all their uniquenesses, and this is what we're going to learn about today. Why don't we dive in a little bit about a background of you, and then we'll get into the little bit of history of your company.
Sure. I joined Frascolds almost 20 years ago. I started as an R&D engineer, so on the test lab, a lot of hands-on and nightmares on on compressors. After that, I started to design compressors, mainly screw compressors at the beginning, but then following pretty much all the projects that were going on in Frascold. In the 20 year, I left the company only for a small window of 5 years for another working experience in another compressor manufacturer in Italy. But then I came back like 11 years ago,
Okay.
and now I'm here in the US. Try
Awesome, growing
to
it.
Yeah,
I'm assuming like over the years, 20 years working designing, you learned a lot. You know what I mean? Because I know that we were talking earlier. You traveled to China, India, all these different countries, and and just learning and expanding the brand. How was that experience from starting out 20 years ago to now, and what have you seen the developments have changed?
well, the learning is a never-ending curve. So what can I say? I try to get in every experience a little piece of my growth, and this is what I'm getting here. I mean, I've trying to learn how to measure refrigerating capacity in HP refrigeration or in BTUs or in tons. So this is
Yeah,
gonna be
yeah.
this is gonna be another piece of my growth for sure.
Yeah, I love that too because I've met when I started out in the trade, a lot of people would say, "Oh, I need a 1.5 horsepower or 5 horsepower." I'm like, "What are you talking horsepower?" Right? So I tried to figure it out because when you were doing air conditioning or whatever, it's normal. 1 horsepower is
Yeah,
1 ton. But then when you
yeah,
get to low temp, it's like, "Oh, I need a 3.25." I'm like, or two, and I'm just like, "What?" And I still, to be honest, I've looked at numbers people showed me, but it still doesn't understand when you got BTUs or kilowatts. Okay, I understand that stuff.
yeah. So fortunately, I'm not the only one.
And I know I feel we know a lot about compressors, and that one's a
Yeah,
difficult
yeah.
one for us. Awesome, awesome. So let's learn a little bit about your company and find out
Yeah,
about what you guys are doing right now.
yeah. Let me try to share my screen. So
Yeah, please do. And those who are listening on the podcast will walk through any of the slides that um, may be a bit more technical.
okay, so I think you can see my
Yep.
screen now, Trevor. Okay.
Yeah.
So, as we discussed today we'll try to go through a brief overview of Frascolds, and then the idea to show you guys, but without boring you too much, what is our series of transcritical and subcritical compressors. So, and then we show you a way of controlling the capacity in the CO2 compressors without the use of a VFD, so it's a mechanical capacity control. And then we go through our CO2 calculation tool that is, in our opinion, a very powerful software.
Love it.
So let's start from Frascold. So you said that you don't know Frascold, but Frascold was, you don't know much about Frascold, but Frascold was a company founded in 1936 in Italy, in Milan. And the headquarters is now in Rescaldina, that is right outside Milan, close to the Malpensa airport. So this is our main operation. We manufacture more than 70,000 compressors between screw compressor and reciprocating compressors. And let's say still 90% of the production is in Rescaldina, Milan. Of course, compressors are shipped all over the world, but we have operations here in the US as well, as I said, here in Jacksonville, where we have not only a stock of compressors, but we have a full operation, I would say, because we have a technical department, we have an after-sales department, so we can tear down compressors and do almost all that our main office in Italy can do. We cannot manufacture a machine, but yeah, we can do a lot. And then, of course, we have also India and China for following the local market. Actually, we have a relatively small production of compressors in China as well for the local market. But in terms of products, we do not manufacture only CO2 compressors, but we do have a full range of single and two-stage compressors for fluorinated refrigerants. So from the fractional of HP up to 80 HP on the reciprocating side. And we go as well up to 40 HP on the two-stage compressor for, lower evaporating temperatures. They come already with an economizer, so the compressor is fully equipped with the economizer as well. Then we have a CO2 series that we'll go through a little bit today, the subcritical and transcritical. But on the right side of this table, there is also our screw compressor production, in which I was involved in my early career. So we have the compact screw compressors and screw compressor for medium and low temp, as well as open type for ammonia. So the full range of compressors, of course, not the CO2 and the ammonia, are rated also for the use with hydrocarbons. So mainly propane, isobutane, and propylene is not the topic of today, but it's also a growing and very big world.
Yeah, so that's a good point, because a lot of people are like, well, propane is new, and there's a lot of regulations on, especially in commercial applications, you can have 150 grams or 500 grams, 300 grams, very small. But when I talk to my buddies that are industrial, they've been using propane for 20, 30 years, hundreds and hundreds of pounds. So these screw compressors, for example, we use in our 290. So, and you were mentioning to me that you have a bigger lineup for propane. Why don't we talk about that just a little bit before we dive into the CO2 and some of the applications you may have of our 290?
Yes, sure. As I was mentioning, for this series of compressors you see on the left, from the fractional, starting from alpha HP up to the compact ones that we see here on the right, that goes to 310 HP. These compressors are rated already for propane, and we made already a lot of application here in the United States. Believe me or not, it was much easier than I thought. Especially the last one we started up was with this compact screw compressor, actually 3 of them with 70 pounds of propane per circuit. Of course, the system and the charge has to be confined. Is an outdoor installation. There are a number of safety to be followed. So it's not that you can put 70 pounds inside a supermarket, but but it is possible. So for the pharmaceutical and the plastic extrusion, there is a lot of market for this compact screw compressor with propane. Even because you keep the system very, very simple at the end, you have a built-in oil separator. So you build like a standard chiller with 2 secondary fluids because you try to keep the charge confined in a machine room that is usually external, like a containerized machine room usually. And I mean, it's easy. The only thing that gets out is glycol or water according to the temperature.
Yeah. Yeah, and
So,
that's pretty cool because we're going to see more and more of those applications as more rules and regulations come into play, more higher GWP refrigerants getting phased down and phased out. And I know for sure that we'll see a lot of more of those applications as the rules and regulations continue to come in and like I said, regulations, because I see even different states are still updating them. They're starting to change
yeah,
it to make it easier and understand all, because it's all about safety, right? At the end of the day, we want everyone to be safe.
yes,
But propane is just, or R290 is another refrigerant, just like CO2 that we're going to talk about. It's another refrigerant. Doesn't matter if it's 22, 404, CO2, R290. You have to be safe with all of them, and that's why we have skilled refrigeration mechanics and technicians working on this equipment.
yeah, correct, Trevor. Since you mentioned about the CO2, I mean, don't forget that we can have still CO2 and propane in conjunction. I mean, we have seen a lot of application in medium low temp where the CO2 is pumped into the machine room, and we have on the compression side propane or ammonia, for example. So we still have all the advantages of the smaller pipes, of the heat transfer, but only pumping CO2 into the cold rooms. So
Yeah, that's awesome.
yeah. So, but the topic for today is CO2, we said. So if you agree, we can jump to
Yeah,
the
let's do it.
CO2 series. So we have, as I mentioned already, the subcritical models. We have 4 main family according to the power of the compressor. So we call our compressor on by letters. So usually the A will be the smaller model and the S will be the larger, and so on with the other letters of the alphabet. So we go from a small 2.5 HP on the A series subcritical. Then we arrive to the newest S model that has 30 HP motor and 2000 CFH. What are the main characteristics of this compressor? They are all splash lubricated, so they don't have oil pump at all. And yeah, the standstill pressure is 1160 psi. That is, let's say, quite standard for the subcritical application and for the ambient temperature reachable in a machine room. Differently, if we jump to the transcritical models, we still have 4 family, in this case, the VQ, S, and the ZTK. So starting from 5 HP up to 50 HP. In this case, the last compressor model on the Z body, they all have an oil pump differently from the other ones.
Yeah, why don't we talk about that a little bit? Because I see this on almost all CO2 compressor manufacturers. Like like a lot of them have the splash, or most of them do, but when you get up to that 50 horsepower, the bigger ones, they need a pump. Can you explain why that is needed?
Well, it is mainly for the distance that the oil has to travel from the place where it is to the last lubricating point. So it's like a piping on the small compressors on a 2-cylinder. It's pretty easy to let the oil reach the crankshaft and the piston rods. Pretty easy. But when we start to talk about a 6-cylinder, where, you know, maybe the last piston rod is far away from the injection point, we definitely need some extra pressure on the oil side to reach the last lubricating point. And actually, this is what we do. I mean, we set those oil pumps with a maximum operating pressure and usually with a bypass valve that is, you know, allowed to reach at least a certain level of pressure that is capable to lubricate the last point to be reached in terms of distance. So this is the reason. But if we can, like for the 4-cylinder, even for the fluorinated refrigerant, we like to keep it simple. So less moving parts. The splash lubrication is really a reliable way of lubricating the compressor once you have the know-how of, you know, building the lubricating pockets, all those tricks for keeping the oil ready at the startup. I mean, this is the way we go.
Yeah, and it's important to understand because most compressors do fail because of some sort of lubrication issue. And it could be like washout, flood back, whatever, overheating, breakdown to oil. And it's so important to understand the oil inside the compressors and how it's working, the temperatures, a lot of different stuff. And we'll get into maybe a little bit of that later. So, but thank you for explaining that.
Yeah. I try to put together some, let's say, main benefit of feature of our compressor. Maybe we'll stop on the things that I think are diverse from our competitors. I think it's pretty easy to everyone that CO2 was a game changer on the dimensioning of components.
When I see that for the first time, going from like a big piston like this, and then you get a little tiny piston, you know, 4 inches to 2 inches, whatever it is. And I was like, I was super surprised. And this is the same capacity. Yeah, same capacity. I'm like,
yeah, correct, Trevor. And this is the reason why all the, I mean, you can see a lot of features that the standard compressor don't have, like particular finishing on the piston rods, on the bushings, and also the finishing of the surfaces of the crankshaft, for example, are crazy compared to the other compressor that work for a lower pressure. You can imagine how important it is to have a super finished surface when those you know, pressure difference are involved, and you know, every single scratch can be the start for a crack. So yeah, you need to pay particular attention to that. And well, since I mentioned the pressure difference, we all know that the pressure ratio of a CO2 compressor is pretty much the same of the other refrigerant, but the pressure difference is actually an issue. And this is why we have 3 piston rings on all our transcritical compressor. So the idea is try to minimize the leakage between the outside the pistons, therefore between the piston rings and the bore diameter of the compressors. And we saw also on this that there is a lot of development behind, because there is a point from which it doesn't mean that if you put like 7 rings, you get a more efficient compressor, because of course the other side of the medal is the power consumption that's increase. Therefore, there is always a balance. What else here? All the compressors can be driven with a VFD. So we'll talk about another capacity control in a while, but they can all be driven with a VFD, usually between 30 and 70 Hertz, according to the operating point. Probably on the right side, I would like to stop about compressor serviceability, because all our compressors come standard with a protection module that is also a diagnostic component. So I think it's nice to stop a second on this.
Yeah.
So this is how the protection module look like. I mean, they are different for what we have discussed, because on the Z compressor, on our largest compressor, we have an oil pump. Therefore, the second module below is capable also to control all the oil pump parameters. But both of them are capable to record and control the number of switching cycle. They will check the discharge PTC and motor PTC. They will also record in case of manipulation, you know, how much we like when we are doing service to put jumpers. And so, yes, this is something that will be recorded in the module as well as a manipulation. And all this information recorded can be, we see later, stored and downloaded with a smartphone with a Wi-Fi connection. So
yeah, and I think that's important too, as a technician in the field, when you're going to do service or you're going to check this stuff out. Lots of guys may not know, or technicians may not know, that you can look this stuff up and you can read the data. And this is how you troubleshoot. You got to understand what the data says, right? So you got to dive in and look at that stuff. So important.
Yeah, yes, correct. Well, at least when you go, and if you have a compressor that is not running, you can directly understand why it's not running, what was the last alarm, and before, you know, trying to power back the compressor, you try to understand what was the reason of the shutdown.
And those devices are Cree1. Can you just download an app for Cree1 to get that information?
Yes, actually, there is an app. That is what we show here on the next slide.
Oh, okay.
That will give you easily a report. You just need to get a cable via Bluetooth, so you don't need to directly be powered to the model itself. And well, it gives a number of interesting informations, like for example, the last 20 events or the last 7 days of alarms. They give you the number of start and stop, how many starts in 1 hour the compressor has tried to ramp up, and all, you know, all this kind of information. Of course, also about trips on the PTCs and oil pumps as well. So it gives you already an idea. I think it is important because in the past, especially, I go just back 1 second, because in the past we know how tricky the PTCs are. So, and especially when they are connected in series, like it was done in the past between the motor and the high discharge temperature, you never understand where the alarm is coming from. And so whenever you try to measure after the alarm, they already cooled down. So the resistance value is back to normal. So it is nice to have a device that is recording what's really happened before.
Yeah, exactly. Because you could sit there for hours and it won't trip again. That's the thing.
Correct.
You have to sit there on a bucket for 3 or 4 hours, and then, oh, there it goes. By that time, you're already back home in bed.
Correct. So this is pretty much what we have on the series. So if you don't have question here, or if you want to keep the question for later, I will jump to the.
I do have a question. When you talk about start and stop, is there a number that you guys recommend for your guys' compressors? Is it like 10, 6, 20? What how many starts?
It depends on the motor power, and usually it's between 6 and 8.
Okay.
But Trevor, is not always mentioned that for a compressor manufacturer, it's important to keep the more than the number of starts. It would be important for us to keep the compressor running for at least, we say usually 4 or 5 minutes, because we know that the startup of the compressor is the most critical moment of its life, because it's starting at the end almost without lubrication. And if you stop it right after and you try to restart it right after again, it's 2 starts without lubrication. So it is.
And that's the big thing, right? It's,
yeah,
you don't see inside the compressor if you're working on it, and okay, it starts, it stops, it starts, it stops. Okay, that's fine. Oh, it starts and runs, and then it's fine. But a little bit of damage happens each time. And this is over time, it compounds. When I worked at the compressor manufacturer, I seen that. You know, oh, scrolls they can flood back a little bit, but no, you're damaging the compressor every time you do that. Oh, but it still works. Yes, of course it works, but there's 1 year off its life. There's another year off its life, or whatever it is. So it's important as a technician to understand when you run it with no proper lubrication, or you overheat a little bit, or you do have flood back. That's causing damage, and it compiles over the years.
Yeah, correct.
And you know
Yeah,
all about it because you see those compressors come back and you look at it and you're just like,
yeah, yeah. And it's yeah, and you know, it's never easy. We say that it's never easy to understand what happened to a compressor when you only see broken parts, and you do, and you don't have any information about what's really happened into
it came
the.
like that. It was like
Yeah,
that.
yeah. We never started up.
Yeah, yeah, I know. I
Yeah.
love that.
No,
I
actually,
always loved the ones where they were like, no, it didn't run from day one, and then all of a sudden it seized. You know, it's a seize, no lubrication, so there was no oil in it for sure. And they ran it. It's like, no, that was DOA. I'm like, DOA. There's not many. Does it happen? Yes. Don't get me wrong, but the chances of it happen are so slim to none because just the quality control all the manufacturers like your company has is is eminent. That's why you continue to sell lots of compressors, right? And you guys
Mhm.
all have good capacity, quality control. And it's just funny to see after I worked the manufacturers to see that, and then it come it didn't start up, and then you put it on the bench and it runs perfectly fine.
Yeah, yeah. No, actually you're right. I mean, is well, we do of course test like for the other refrigerants, we test 100% of the compressors, and we can supply the running certificate of every compressor. So that's why when I soon learned the word dead of arrival, as you say, it's here in the US. But you know, when you show to the customer that the compressor has been already running for 20 minutes before the delivery, I mean, I'm not saying that it's impossible that a
No.
compressor can fail at the startup, but let's say that is at least rare. Or
Yeah, I would say it is too. But it could
yeah,
happen. Don't get me wrong. It
yeah,
definitely could happen. You don't know what happens from the manufacturer to that site.
correct, can happen. It's not impossible. Good. So if you agree, I will jump to the to our Capaflex capacity control.
Yeah, let's do it.
Yeah, so it's what is Capaflex? Capaflex is a mechanical capacity regulation that can be installed in all our CO2 compressors. So in CO2, we hear a lot of times talk about VFD, but we don't hear a lot about mechanical capacity control. And I think that the main reason is because it's very difficult to design something that it really works, probably. But anyway, so this is how it looks, our capacity control for this compressor. So this is a cutaway of a real compressor. Is a 2-cylinder on the left and only one cylinder, I think, on the right. And yeah, so we will see in a second why and when the Capaflex in a CO2 system makes sense. So we see that in a single compressor, we can reach a wider operation than a VFD, for example. Typically, a VFD, we'll see later in a graph, can regulate maybe down to 25, 30 hertz. That means if the maximum is 60, could be probably 50% of the capacity, or if it is 70, it's probably 45 or 40% of the capacity. So this system will allow to go as low as 20%. You will see that I will not try to sell the fact that a VFD is a less efficient of a Capaflex. They are just different. So as always, we say as engineers, there is space for a VFD, and there is application. There are applications in which the mechanical capacity control can make sense. So we just want to show what it looks like, and then it's the engineer that will decide which one is the technology that fits his application.
And I totally agree with you there because I have over the years I have so many people arguing, oh, VFD is better on the compressor. No, digital is better on the compressor, and they're just different. And different applications will depend on what you want to use, and because there's a lot of costs involved, and then complexity sometimes as well. If the people do not understand how to set up a drive and wire it, it's gonna probably cost the customer a lot more in the end than having a capacity control that's mechanical. You know what I mean? If they understand mechanical,
Yeah,
open, on, off, on, off. So now, if I had that, people just argue with me all the time, or just say, no, Trevor, digital is not, or Copeland calls it digital, you call it
yes, yes,
Capaflex,
no, no.
and then it's different technology. So, and I've seen people prefer one and the other over it, and I'm like, it's whatever works the best for you, your customer, and the people working on it at the end of the day.
Correct, correct. So that's why in this at this point we are saying that I mean, it is a stepless capacity control that can make sense, for example, when we are planning to use a VFD for like few hours. So we can start to say it doesn't really make sense probably to invest in space and money, since we are already planning that it's gonna work for a few hours on a seasonal base. So what else? I mean, it's easy to install. You just mentioned that it doesn't need to make a rocket science modulation. We see later that the parameters to be controlled are very few, and it's still a mechanical head that has to be installed on a compressor. So something that we are all used to do with the old capacity systems. In the design of this component, we try to, let's say, eliminate, of course, we were not able, but let's say that 95% of the possible failure will leave the valve in order to have the compressor running at full load. So even if the system is not working, so in 96% of the cases means that the compressor will run at full load. And yeah, it is a compact solution. So we saw that this component had a lot of success in Europe on transport, for example, where there is no space and not even the capability of installing a VFD in most of the cases. Let's think about buses, for example, or yeah, mainly train and buses in which the VFD is not really loved by the engineer for many reasons.
Yeah.
So this is how the capacity control look like. I mean, we have a magnet usually on top. We have a valve unit and then a cylinder head. So here on the left, we can see where the valve unit is. So this is the suction channel. So there is the magnet on top. And this is the configuration of the compressor. So this is the suction channel. This is the suction side. We have the discharge side on the right. We can recognize about the position of the reeds, so the suction reed and the discharge reed. And then we have the discharge line. So in this condition, the compressor would be working at full load. So the gas is going through our capacity control valve. And as we see, the gas will flow through the suction reed and then to the discharge reed. So as a standard compressor, nothing different. This is not a rocket science. But if the valve goes on, as we said, the valve will close the flow on the suction side. That means that the compressor has zero sweat volume in this moment. And then, of course, if it is pulsed off, we will have the full load again on the head. So very similar to what we were using on the fluorinated refrigerant. The main difference, let's say, is on the control side. So on the control side, we would use a PWM controller for this type of system. The main reason is to keep the cycle in a period usually of about 12 seconds. I think we understand why. We saw before that whenever we keep the valve totally closed, sorry, let me try to show you again, we can understand that the piston is trying to pull vacuum from the suction chamber. That is not really something that the compressor likes. So that's why we try to pulse in time that is, we found the optimal of around 12 seconds in order to guarantee to the compressor also the right lubrication and the reasonable overheating of the components. So the remaining game is made by the controller, because we saw that when the valve is off, we are at full capacity, and when the valve is on, we are closing the suction side. So it means that on a period of 12 seconds, for example, if we are keeping 3 seconds off and the remaining on, we have 25% of the cooling capacity for that head, of course. And if we are doing, for example, like the example below, 6 seconds on, 6 seconds off, we'll have 50% of the flow for that head. So quite straightforward.
Yeah. Yeah. So that's one of the things about having capacity control like this. It's very simple. You know, when you think about it, it's on, off. Do I need it or not? So, and then you just need the signal going back to that specific controller that controls those.
Correct. And as I was mentioning before, probably the main difficult part for these components is the development, because I mean, it's a project that was lasting, I would say, as much as the compressor itself.
I believe that. I definitely believe that.
Yeah, in order to have something that is reliable and efficient as well, because I show you a graph that it has to be efficient in order to be interesting for the market as well. But here, just to show what we are saying, I mean, we had to equip all the compressors for the field test with high speed response pressure transducers in order to check that the sealing of that piston was still working, because we are talking about higher pressure difference again. So if one of those O-rings or part is not sealing anymore, end of the game, we'll not have the capacity control anymore. So this is on the picture here is how the real system looks. So when I was talking about the O-rings, I mean, these are the sealings. So here on this slide, I just want to show you a little bit what was the design phase of the component in the past. So what we did, first of all, on this chart, we have on the x-axis the capacity of the compressor, so from a theoretical 0 to 100%. On the y-axis, we have a relative COP. So the base compressor is the compressor that has the COP calculated or measured in this case at full load. And so what we did, we made some measurements with a VFD down to 50%. So in this case, we were running the compressor at a maximum of 60 Hertz, and this will be roughly 30 Hertz of frequency, therefore half the speed. And we saw what was the relative efficiency of this compressor. So even with a VFD, so the curve is not flat, you are still losing almost 15% of efficiency, because you go as down as 85%. So we measured on our very first prototype that we were capable to reach 70% of the efficiency. So we said, this is a good starting point. Let's go ahead and try to see if we can do something better. So we fixed our, let's say, threshold for the go or not go of the project at an efficiency that was 80%. So not really, I mean, still lower than a VFD, but still interesting for the all the other reasons we have just discussed. And so from our simulation, the red curve was what we were capable to reach on a theoretical basis. And fortunately, the tests were not super far from this value. So we saw that we were capable to reach 83% of the COP at 50% of the capacity.
Wow.
So, and this is what this system is capable to do with two heads or one head. It depends on the step you want to achieve. That is the one on the left, and with a PWM controller that is usually something you can get from off the shelf or that we can supply as well in case.
Yeah. So, and that's important to understand. That's pretty cool that you can get that type of COP at 50% capacity. And so, just to be clear, so you played around with how it loads and unloads the compressor to get to that. Is that was your main thing, or did you change the design of the? You might have mentioned it. Change the design of the head to get that increase in COP.
No, I was not mentioning, but you are right. I mean, this is what we did. I mean, we had to optimize the pressure drop through the valve, for example. And another thing that has been optimized in the versions are the sealing between the high pressure and low pressure, because again, the pressure difference is crazy in the CO2 application. Yeah. So trying to do a sealing with an O-ring is not the easiest thing anymore. And so these were the two main improvements that we made on this. Awesome. So after the measurements, we obtained these tables that we are usually sharing with customer to show what the technology is capable to do. Of course, the 0 is a theoretical value because we consider 20% as a minimum capacity step.
Yeah, because if you start to go lower than that, and you can run into lubrication issues or overheating issue potentially, whatever it is. It's something that you want to keep it in a safe environment.
Yes, correct. And of course, all the inefficiency that we have seen are translated also on a limitation on the application envelope, because of course, when we're talking about an inefficiency, we always get that an inefficiency somewhere. And in this case would be on the isentropic efficiency of the compressor that is translated into higher discharge temperature. So
I love this. I love that you're showing the application envelope. Every compressor has one of these, and manufacturers have this. This is what you got to look at. I'm real glad that you're showing this, because this is something I didn't know about as a technician. Application envelope, compressor envelope, operation envelope. Didn't know what that stuff was. But this is the most important thing for a compressor. By far the most important thing. And so anyone out there, if you want to learn about compressors, check out their application envelope of the compressor so you understand where you're running and why you're running there. Because those of you listening, there's a lot of different colors at different percentages of the capacity control. And if you're outside that, it's going to cause damage to the compressor.
Yes, correct. I mean, this is not a sale tool, but it's definitely an engineering tool. I mean, we need to show where this inefficiency is. I mean, it's shown, so it must be shown somewhere because it's thermodynamic. So it's the first law; it has to be shown somewhere.
Yeah, and it's great because it's something that more people need to get an idea of, because you might have a big operation envelope for your compressor, but depending on where you're running that compressor, the design conditions, you might be running outside the envelope, even though the envelope is that big. And
yes, this is
because I've had lots of conversations with technicians, and they're like, well, Trevor, isn't this the operation envelope? Yes, it is. But in these design conditions, it's not. So
I
like that.
Yeah, correct. Yeah, so this is our capacity control. If you don't have any other,
I do have a couple of questions. So on that last one, you had a 10K superheat. Is that for both subcritical, transcritical, or is that just for your transcritical compressors? And 10K is 18 degrees Fahrenheit for anyone to know the units.
Well, yeah, I mean, it's if you see on our selection software, this is our standard superheat we put for both transcritical and subcritical compressors. I mean, there is a lot of talking as usual on superheat and even more now on CO2 because we all know how the solubility of the oil is affected by CO2. So it's, I mean, it's clear that the POE oil can be diluted by CO2 by far more than other, refrigerants and oil. Therefore, it's always important to guarantee at least a minimum superheat. But on the other side, we are trying also to go in the direction of some customers that are trying to float as much as possible the evaporator, especially in some applications. So they will never guarantee you the 20K we would like to have. So it's always a compromise. And then, of course, on the other side, we don't even want very high superheat because especially on our application, they can result in a higher discharge temperature, especially when Trevor, especially when the suction of the second stage compressor is the discharge of the first. So we wanna stay somewhere in between.
Yeah, and that's one of the uniquenesses of CO2 when you start to learn about it, that you gotta have a minimum superheat, but you also want to keep your discharge temperature down. So it's a happy medium, especially for designers out there, right? It's something that you need to really take special care looking at, that for standard refrigerants that are there now, HFC, HFOs, you didn't have to really look at that as much. I guess the HFOs run a lot hotter than the HFC refrigerants, but it's something that you gotta be checking every time. It doesn't matter what compressor it is.
Yeah, correct.
Or whatever refrigerant it is, I guess.
Yeah, well, it is refrigerant, it is compressor, and I mean, again, especially on two-stage system or booster system, I mean, you have always to keep an eye. I mean, as a compressor manufacturer, I'm not the one that I would say the higher is the superheat, the better is for the compressor. Not at all. I mean, an high superheat is dangerous as much as liquid entering the compressor. So we have to be in a range of a reasonable parameter on that
Yeah.
side. Yeah. Good. So if you agree, I jump to the our calculation tool, our seasonal calculation tool. I will show you what we have on our selection software that can be downloaded for free on our website. So it's not only a selection tool we will see, but it's also a seasonal calculation tool that can, allow you to understand how your system is operating in different climate zones. So what can we do or simulate with our selection software? We have a list of the most common layout. First of all, this software is in continuous development. Since it's internally designed and programmed, there is always an update every release because a customer is asking, can you add us heat exchanger here, an heat exchanger there, or something like that, So it's a never-ending project. It's like the learning curve
Yeah, exactly. I love it.
We were talking about before. So these are the most common layout we can simulate. So we can simulate booster system, parallel compression, low temperature systems, only low temp, multi-level evaporating, and we can add a lot of heat exchanger around the system. I will try to show you briefly without annoying you guys too much. So the possible configurations are the ones shown here. So we can do booster with we can simulate booster with parallel compression, or a simple only low temperature system, or we can add up to 4 different temperature level.
And is that what you meant by multi-level evaporator? You can have different Temperature.
Yes.
Okay, I get you.
Yeah. Then we can add a certain number of heat exchanger on the flash gas line. So in the years, there are, how can I say, many different configuration. But again, every configuration has a reason for a specific application. So there is not one that is right and the other one that is wrong. They are only different in different
I like
part of the
that.
circuit, but yeah, they all have their own sense. So we can add it on the liquid line or before the back pressure valve or right after at the intermediate pressure. So this is what the software allows us to do. And then we were talking about a certain number of heat exchangers because we can add a lot of heat exchanger. Fortunately, they can be add or taken out so you don't have a headache every time you try to select a compressor. But from going counterclockwise, we can have like heat recovery, like in this case. We can add air conditioning to the system. We can have a superheating for the parallel compressor. We can add external subcooling for increasing the title of the liquid entering these cabinets here. We can have this is sometimes a life-saving for the compressor, the internal heat exchanger on the gas suction line of the low temperature compressors. Or this is the life changer of the life saver actually for the compressor of medium temp, because if we have too high suction gas superheat here, we can lower the temperature with the superheater that can be like heat recovery. Sometimes we have seen it a lot for floor heating, for example, on low temperature application. So it is heat that can be recovered.
Yeah. And that's what's so cool about CO2 and like this. I like the software because now you got air conditioning, you got heat recovery, you got subcooling, you got all these different protections as well. But this is a full solution now. You know, you can use one refrigerant to do a whole building. I was at a site a few weeks ago, or last month, I guess now, that's what it was. It had it all. One CO2 system was doing everything in the store. It was amazing to see. Is it complex? Yes. Is it doable? Yes. Can you learn it? For sure, because people are doing it, you know, and everything's learnable, and I like that. And that D superheater, I think that one's pretty cool too. I'll definitely have to check out the software.
Yeah, yeah. We actually made an example here because I said it's not mandatory to have all the heat exchangers all together. So you can select a very simple system here. As an example, we try to simulate a booster system with a parallel compression, a very simple example for giving a look of how the software works. So we try to select for a 340 kBtu per hour at the medium temp, 85 for the low temp, and then we added some air conditioning, 270 kBtu on the air conditioning side. So as said, the software may look a bit complicated at the first sight, but it is a selection tool, first of all, so we can select our configuration. That is what we have discussed. So this is a booster system with parallel compression and with an air conditioning. So we keep on adding stuff that we need, like the flash tank, like the air conditioning in this case. And then since it is a selection tool, we put a refrigerating capacity target that we want. And we run the selection, first of all. And what we get is the number of compressor and type of compressor that is capable to deliver the capacity that we have asked to the selection software. And it's giving us also the real capacity that is delivering. Of course, we're not matching the exact number we are looking for, but pretty close. Then, of course, you can refine your selection by changing a compressor. For example, here we are selecting compressor that is delivering the capacity all 70 hertz. Probably it would be wiser to select a bigger size of compressor that is delivering the capacity at 65 hertz instead.
Yeah.
So this is something you can refine, and after you run the first selection, that gives you a rough idea of what is giving you the capacity you're looking for. I think the tool is pretty cool because it's giving you also on a real time. If we have time, we'll redo it together live.
Sure.
It'll give you the pH diagram of the system you have just selected. So these are your real working points and your real pressure, temperature, enthalpies, mass flows, and everything that is needed for the calculation of the thermodynamics on this point. What is cool, since we have been discussing about discharge temperature, already the pH diagram, in our case, give us two different color at the temperature that is usually allowed without any cooling. So typically we say 284 Fahrenheit. As long as you stay below, you don't need to do any cooling, but as soon as you jump that temperature level, the software will give you an alarm first. And then on the red, when you go on the black side of the ISO thermal cards, it will tell you that the temperature is too high, so the selection is something wrong.
That's pretty cool.
Yeah, and then what we can do with this tool, we have just selected that system. So we have the compressor, we have the capacity. We can jump to the seasonal calculation. So on the seasonal calculation, the software, well, first of all, the seasonal calculation is the only thing that is not free for download. I mean, it means that we will not let the customer pay, but we just want to get usually a request for the seasonal calculation, and we give a code to be added to the software. I would suggest if anyone wants to play a little bit with this tool to ask us, to inquire us, because I will show you that it's a very powerful tool. So you can choose your location. In this case, we selected Toronto. And so there is already a lot of cities that are preloaded into the software. So we do have already a profile temperature all over the 8,600 hours of the year. We can, of course, select a lot of parameters inside. Like, for example, I would like to mention the high pressure control strategy. We'll see a little bit that's in a lot of application, we will jump from subcritical to transcritical. So it's nice to define for the seasonal efficiency what is the strategy you are following, because it makes difference in the efficiency point of view. So every load here can be defined as constant. So it means that we can have a certain level of refrigerating capacity equal all over the year round, or we can change it to linear. That means that we can make it also dependent on the ambient temperature. And we can do it for every single load we have in our seasonal efficiency calculation, just to refine the calculation. So we can keep it constant, or we can let it vary according to the outside temperature. On the high pressure side, as we said, there is a control strategy to be defined, and this is how can I say, it's a big challenge, because it makes a lot of difference. So we do not have to forget that that system will not work transcritical all the time. Actually, in the Toronto example, we'll see later the number of hours in transcritical are pretty low.
Mm-hmm.
And so we have to define a control strategy, and you can decide. We have a preset control strategy in our case that is, of course, On the first zone is guaranteed that the compressor is working above the minimum pressure. Then we have a zone in which we will control, let's say, easily the subcooling like a standard system. And then there is a transition zone in which we still control the pressure, but we keep a linear temperature between the transcritical temperature and the temperature we decide for dividing the zone. So this is a smooth transition to the transcritical control, where of course then the pressure is optimized together with the gas cooler outlet temperature. So we do have a preset parameter, but everything can be then changed in case. But even if you keep it like this, you can already run a seasonal calculation and see how your system looks like all over the year. So that means that the output will be on the year, on the hours of a year, how your refrigerating capacity, power consumption, and all the other parameter change.
No, that's pretty awesome,
Yes.
because that's real important, especially that last slide that you were showing, the different zones, because this is something important about CO2 compared to all the other refrigerants. You don't really talk about all these different zones that you have, especially when you get up into supercritical and transcritical. And it's nice that you explained it like that, because there are different zones and your system is going to work differently. Because not only you got to worry about when it's really, really hot out, when you're in supercritical or transcritical, you got to worry about when it's really, really cold out as well. To
Correct.
keep that system up and running, because those compressors will shut off.
Correct.
Awesome. So that's pretty cool about this seasonal calculator.
Yeah, and I think this is our second last slide. We ran the same system last week to see how it was behaving in different cities around the United States, just to see what would be the difference between Toronto, Denver, LA, and Seattle. And it is pretty interesting that the same identical system will show a pretty different seasonal efficiency. Of course, in this system, we only had air conditioning, for example. And if we see, for example, this is the load for the air conditioning, it looks to be pretty low in Toronto and Seattle. But again, the number probably of hour at higher efficiency for that type of system are, let's say, much bigger. It's a much bigger number in one city more than another. So
Yeah.
this is telling us that one system couldn't be the solution for all the cities in the United States.
Exactly. I love that, because that's so important to know. Understand, you can't just take a system and just plot CO2 system and just plot it in, and really any system, because they're going to run differently in what that ambient is, the conditions, the humidity, all that.
Yes. So this is our tool, and my last slide about our tool. That's as we said already, it is important to not to keep in your books only the worst scenario, because we'll not tell you what is the reality of your system. I mean, otherwise it wouldn't be called the worst scenario. If we dimension everything on the worst scenario, probably we are making mistakes when we are running the system at part load, for example, or when the outside temperature is far away from that point.
Exactly.
Yes. And what else? I think it's nice, the possibility of evaluating all the heat reclaims or all the air conditionings, because it's not said that, for example, a space heating is convenient in all the cities. Because we need, for example, to force the compressor to work transcritical when it's maybe not necessary, or so all these things can be evaluated and calculated.
Yeah, that's awesome. That's good that you have a software that can have the capabilities of doing that.
Yeah.
This was very informative. Like I really enjoyed learning about these different, well, the different calculators. That's really good, as well as the different systems, compressors that you have. How can people get a hold of you, get a hold of your company, learn more about Frasco?
Uh, well, you can visit our website. We are always present in all the exhibitions here in the United States. So the next one will be a heating and cooling show in Chicago in a couple of 3 weeks, actually. I don't remember exactly the date, but we are pretty much present around. And
Awesome.
and
What about, I do have a couple questions here. Do you have a distributor in Canada? Do you have any distributors in Canada?
well, as we do have a person, we have a salesperson. Yes, I can definitely put the person in contact with.
Awesome. Awesome. Well, Matteo, I want to thank you so much for taking the time to give us a brief overview of what you have for CO2 options and the different opportunities you have here in the North America. I do have another question for you. You said that you do inspections here in North
Yes.
America. So one of the things that I've always heard is what's the turnaround time for those inspections? Because I used to get this question all the time. And then what is the warranty for the compressors? So do you guys inspect every compressor if it's under warranty, or how does that work?
Yeah, our standard warranty is 2 years, and we do definitely inspect every compressor under warranty. And we try to keep it in 4 weeks from receiving. So we
Awesome.
are committed to supply a report in 4 weeks from compressor receiving. So far, we have been capable to do it. So I cannot say that the market is a compressor killer. So
Yeah, I love that. No, that's good. 2 years, 4 week turnaround time, inspect the compressors. And I think really this is how more and more people need to learn, need to look inside the compressor, oh, that's another question. If it's in warranty, can the technician open up and look inside, or do you guys not want that?
usually we don't. Of course, we have OEM with which, I mean, we've been working for already more than 8 years. And if it is something that we agree, like, hey, can I open ahead because I have the suspect that a valve plate is broken, or, I mean, why not? In that case, we know that we have those kind of relationships. So the customer knows what he's doing, and we are supporting the customer from here. And if we can save time shipping like a valve plate instead of returning a compressor, why not?
Awesome. Yeah, I love that. Okay, everyone, check out the website. It'll be in the show notes. I want to thank everybody for taking the time. Matteo, I want to thank you for taking the time to hang out with me on CO2 Mondays, and I'll see everyone at the next CO2 Monday show. Thanks, everybody.
Thank you, Trevor. Thank you, everybody.
Hey, thank you for watching this video. I do hope it is bringing you a lot of value. If you are looking to grow and build your refrigeration teams and want them to learn CO2 refrigeration, head to the refrigerationmentor.com website, click to contact us, and let us know how we can build a culture around training inside your organization. Let's get a conversation going.